Hello everyone and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry and today I'm going to run through a few undergraduate level, high school level physics questions. So here's the first one. So it's just to calculate the RMS speeds of nitrogen molecules at 25 degrees Celsius and 125. So this uses the Boltzmann average kinetic energy expression. So here we have that our average kinetic energy, I'm just gonna bring this back a bit here. I think I ended up with a large brush size. Our average kinetic energy is 3/2 kT, where this here is Boltzmann's constant. And this, I'll draw this down again. This here is the temperature. So if you look here, so this is kinetic energy, so this is in joules. So Boltzmann's constant is in joules per Kelvin. And now the nice thing is that K is actually our ideal gas constant times 1 over our Avogadro's number. So that is what cancels the mole out of there. So that's 8.314 joules per mole Kelvin times 1 mole over Avogadro's constant, which comes out to be 1.3806 times 10 to the minus 23. So that also means that we can re-express our average kinetic energy as 3/2, or sorry, let's backtrack a little bit. So our average kinetic energy is 1/2 mv squared, where here it's the average velocity squared, and I'm going to stick the squared outside actually. So our average velocity, or our average speed squared, and so that equals 3/2 kT. And so then our average speed is then the square root of 3 kT over m. But as K is our ideal gas constant over Avogadro's number, then this is just 3 RT over m times Avogadro's number. Which would be in 1 over mole. And so our mass, which is in grams, times Avogadro's number is just our molar mass. So this is just the root 3 RT over our molar mass. So that makes it significantly easier to answer this question. So our average velocity, so given our temperature at 25 degrees Celsius, then that is the same as 298.15 Kelvin. And given another temperature at 125, that'll just be 398. our molar mass for nitrogen for N2 is 14.01 grams per mole. There's two of them, so that'll be 28.02. But then we need to multiply by a kilogram per 1,000 grams, as we're going to need this to be in kilograms because our R is in joules. So R is 8.314 joules per mole Kelvin. And a joule is a kilogram meter squared per second squared. So for the kilograms to cancel, we're going to need our mass in kilograms. So our molar mass for N2 is 0.02802 kilograms per mole. Okay, so I think we got all our units figured out, and so we can answer this question. So our average speed at 298 is the square root of 8.314 joules per mole Kelvin, 298.15, and all divided by 0.02802 kilograms per mole. And so the Kelvin will cancel, the mole will cancel, and the kilogram is going to cancel with our kilogram in here, leaving us with meters squared per second squared, which is good, because when you take the square root of that, our speed is going to be in meters per second, which is the appropriate units. So if we run this through on our calculator, we get 515.04 meters per second. And if we repeat this now for 398, then we would get 8.314, 398, and all divided by this 0.02802 kilograms per mole. Moles cancel, Kelvins cancel, the kilograms will cancel with the kilograms and the joules, leaving us with the appropriate units and giving us 595.33 meters per second. Okay, so those are our different speeds at different temperatures. So sketch approximate curves of the molecular speed distribution. So our speed distribution, which is not integrated, so it needs to be integrated to give us our actual speed. But this is the number of molecules at a given speed. 3 halves e to the minus mv squared over 2kt. So these are non-integrated, but it's still, as the integral of a Gaussian is just going to give you a Gaussian back. It gives us our basic shape, so it should follow a Gaussian. Our width is going to be proportional to temperature, so as temperature increases, the width will increase, and this is going to be approximately our prefactor, and so as temperature increases, this guy should decrease. So together, even though this is not integrated, we can still get a basic shape by saying, well, the center of our distribution is going to be at our average speed. So so we're going to have about 515.04, and we're going to have some width, and so we can draw the distribution such that it goes through that. And then at a higher temperature, now these guys are probably going to be sandwiched between each other. At a higher temperature, we're going to have a peak at a lower spot and be a little wider. And so hopefully this looks like some kind of a symmetric Gaussian. And I'm starting to think, there we go. So I think it's a little wider, and it's peaking at a higher temperature. There. So there's my 2 equals 298.15, and my t equals 398.15 speed distributions. So they should be Gaussian, peaking at your average speed, and the higher temperature one should be a bit wider but a bit shorter. That would be an approximate sketch of your molecular speed distributions. Okay, so if we take a look through the solution posted, so it just gives the equation, that's fine. So they get different speeds, but if we look closely, we see they did not convert the molar mass from grams per mole to kilograms per mole, which is going to throw this all off. So your units in the end are not meters per second here. And then they've pasted up some picture of the distributions, which is what you, so these are what the distributions would look like, but so there's a unit error in the calculation, so these are not correct.